torque and angular momentum. So before going straight into the angular momentum part, let us start with the torque and see where we reaches. Now torque tau, we understood it is equal to R cross F. And according to the second law of Newton, force F will be nothing but equal to d by dt of linear momentum P. Okay. So I can write this as this up into the differentiation. You can take d by dt of R cross P. Now the tau is equal to rate of change of L. So I am introducing a new quantity here, that L, which is equal to R cross P, and we call this as angular momentum. Angular momentum denoted by L. So from this equation R cross P, you can see that angular momentum is nothing but it is the moment of linear momentum. Moment of linear momentum. Okay? Or what is angular momentum? It is the momentum associated with the angular motion. You can say like that. Momentum associated with angular motion. Or momentum derived from the torque. So, this is the relation connecting torque and angular momentum. Torque and angular momentum. Alright? And one more thing, you can see that the force F is equal to rate of change of linear momentum. See this? So there is a relation between force and linear momentum, like the torque and angular momentum. They come almost in the same form. Let it be there. We will continue that discussion in another session. So angular momentum L equal to R cross P, and therefore this angular momentum L can also be written as momentum sine of the angle between the two. And you can see that angle theta equal to 90 degree, angular momentum L will be maximum, and that is equal to R into P. When theta equal to 0 or 180 degree, you can see angular momentum L equal to 0. There is a minimum. So the same is applicable to torque also, you might have noticed that. And another point relating to angular momentum is that the direction of the angular momentum. Direction of angular momentum is nothing but it is perpendicular to both R and P according to the rotation. That means angular momentum L also acts along the axis of rotation. That is along the direction of what we call torque. So torque, tau and L both are having the same direction. That is along the direction of the, or along the axis of rotation of the system, you can see. Okay? So these are the points relating to what we call angular momentum. Now let us assume that the equation tau equal to rate of change of angular momentum, F equal to rate of change of linear momentum. Then based on this is taken as the second law of linear motion, then Based on this, we can state the second law of rotational motion there, that the rate of change of angular momentum is equal to the torque applied on it. So when we are getting the equation like this, comparable, there is a connection between the linear motion and also there is the angular motion. So based on this, you can define three laws of rotational motion and also the three equations of rotational motion is possible. Okay? Now, before going into that, let us consider what is conservation of angular momentum. Conservation of angular momentum. Conservation of angular momentum states that for an isolated system, that means for a system not acted upon by a torque, the angular momentum remains constant. So, taking this equation, torque 2 equal to time rate of change of angular momentum L, and if there is no torque is acting on the system, then torque 2 equal to 0, you can find that d by dt of angular momentum will be 0. That rate of change is 0, that means there is no change in L, that means L remains constant. Simple way we can define the conservation of angular momentum. If there is no torque is acting on the system, the total angular momentum of the system remains constant. So this is also very important point to be noted, and this can be applied to what we call the motion of what you see the planets around the sun and satellite around the planet.